test. I sent something this morning, but then I removed it because it was for the other class. There is no vector yet. Okay, you already have enough to study kinematics2d and freefall and just projectile motion, just with a horizontal velocity to begin with. So when you throw something like this, right, initial velocity is horizontal. So on the y-axis, it always starts from rest. So there is no vector yet. Vector is going to be very important for what's coming next. So for physics, make sure for the test, it's on paper, in person, multiple choices. Make sure you print out the equation sheet, right? You can print out the equation sheet and be on time because I'm going to start handing out the test early. And so make sure you catch that bus and you're not late. And what else? You need to practice, right? So in my Dropbox, you have the practice exam. I go over that. You have one folder with all the assignments. I go step by step. And you have another folder where I go through the problems that you find in my slides. So I've been teaching for the last 25 years. So I make it like it's easy, but it's not easy. Okay, it's just because I've been doing the same thing for the last 25 years. That's it. It looks easy, but it's not. Okay, so you really have to practice and practice and practice. So I don't know where we stopped. Okay, so yes, and do remember you have a textbook here. Remember the textbook? I think this is your textbook. And you see here in the chapter 1, so Cotnell and Johnson, chapter 1, they go over trigonometry, right? So you can go over that. They have very nice solved problems. So vectors for next test. And here they go over vectors. What's a vector? How to find the components of vectors? How to add vectors, right? So it's in the first chapter. In addition to that, in Dropbox, you're gonna have 2 tutorials: how to find the components of vectors and how to add vectors. So these are videos I have found on YouTube, and it's gonna be found in Dropbox. So you cannot be like a tourist. You come, you enjoy the slides and you leave. You have to practice. Otherwise, otherwise it's not good. Okay. So last time, so I'm gonna go over vectors. So last time, I introduced vectors. So for example, this is a vector displacement. So remember, displacement is a vector, velocity is a vector, acceleration is a vector, force is a vector, speed is a scalar, distance is a scalar, time is a scalar, energy is a scalar. So here you have a vector displacement, and you can find its x component. So the x component is going to tell you how far west did you go, and then you have a y component, which is north, right? How far north did you go? So why are we using components? Because each component is doing something else, right? Has a different job. So we're gonna get into that, but again, when you are working with vectors, you can print this out. So that was in one of my posts. You can print this out. Okay. So you see you have 2 coordinate system. You have x, y. So that will be the Cartesian system. And you also have a polar graph, right? So you go counterclockwise. You see 0 degrees, 90, 180, 270, 360. Agree? Mm-hmm. Okay, so then when you have a vector, let's say you have a vector like this, first thing you want to do is to attach the origin here to the tail. So the tail is always attached to the origin. And then that point here will be the head. That head here, that point has the x component and the y component. So that's one way you have to describe a vector by its x component and y component. It's just a point here in the xy coordinate system. So that's one way. Do you agree? Or we can use the polar notation. So in that case, we can find the magnitude. So how much? And how can we find the magnitude if we have the x and the y? Trig, or in that case, that would be the Pythagorean theorem, right? Or x squared plus y squared equals hypotenuse squared. Do you agree? And the direction? And the direction, you're going to use tangent, right? So if you have your vector here, you can see you're going to do opposite over adjacent. Opposite over adjacent, that's going to be that angle here. Do you agree? Mm-hmm. Now, if you have a vector like this, right, 150 degrees, okay, you have the magnitude, and you have this angle there, and you want to find the components. So you want to find the x component, here, the location on the x-axis, the y component here, so that will be the location of the y-axis. So in that case, the x component is always the cosine if you use that polar graph, and the y component is always the sine if you use that polar graph. So don't feel embarrassed. You can print this out, right? And if someone says, okay, you have a vector south, so this is west, so south or west, 20 degrees south or west, right? You see that on the polar graph is 210 degrees, 210, right? So if you want to find the x component, see that will be my vector here. X component, you're going to use the cosine. Y component is going to be the sine. Is that clear? Mm-hmm. So you can always print this out, or you can do some art and craft. Okay, if you do art and craft, you can do something like this: 0 degrees, 90 degrees. That will be pi over 2. Here you have 180 degrees. That will be pi. That will be 3 pi over 2, 270, and then 360. Do you agree? Mm-hmm. Okay, and a vector is the tail is always at the origin. That point here, that will be the x component and the y component. You have x and y. Okay? Yes.
Just to be clear, this is for exam 2, correct?
Exam 2. No, and the unit that's coming up. Because we're going to get into equilibrium. Very important if you go to exercise science, biomechanics, everything in the body, the mechanical system of the body works with vectors. Yes, so yes, that's going to be for test number 2. Doesn't mean that you're going to space out right now, okay? You stay with me, okay?
Yeah.
Not everything is about the test 1. Okay, so here, to make sure, simulation. So this is a vector A.
Yes.
Okay, thank you. See, you have a vector A. So that vector A, I can cut and paste anywhere I want. It's still going to be the same mathematical object. So it could be a vector displacement when you move from here to there, or it could be a vector velocity. So for example, if you have a projectile in your hand, you're going to launch that projectile. That could be the initial velocity. Okay, or it could be a force. Imagine that you have a desk and you are pulling your desk like this. So that could be the force. Do you agree? So this is a vector. Okay, it has a magnitude. See, the magnitude is given there. Okay, and it has you always start the angle, okay, from the positive x-axis. If you go counterclockwise, it's going to be positive angle from 0 to 360, or it could be negative if you go clockwise. So if I do this, that will be negative 30. So that will be for the standard notation. Okay? So you see, I can take my angle, my vector, make it like this. Okay, any question? So it has a magnitude, how much, of what, so it could be meter per second, and a direction. Now you see, it has a, so now I'm going to attach the tail at the origin, so you can move the origin here, right? So that point here, okay, will have two coordinates, x coordinate, y coordinate. The x coordinate is 5, so that will be the x component of the vector, and the y coordinate is 10, that will be the y coordinate of the vector. Is that clear? So how do you want to trace the coordinates? So when you have a vector, you go from the tail to the head. First, you're going to run sideways. So I'm going to run this way. That will be my x component doing its own business. And then you go up or down. So that will be your y component. So you see this vector here at the head. The x component is 5. The y component is 10. Do you agree? Mm-hmm. So you have two ways to describe this vector. You can say A, its x component is 5, y component is 10, or you can say the magnitude is, you use Pythagorean theorem. Then here you have a unit, maybe it's meter per second, you have a unit here too. At 63.4 degrees above, counterclockwise from the positive x-axis. Do you agree? So if you are given, like, let's remove this one. So if they say, okay, I have a vector, I don't know, v minus 15 and 5. So what you do, you take first the x component, okay? So that will be your minus 15. The y component here, you make your point. Okay, so that will be the point. The point that you have here, it's going to be the head of the vector. And the tail is always attached to the origin. So that's going to be your vector v. Okay, so you run 15 to the left, and then you rise 5 up. So usually we put 15 here and 5. Do you agree? Mm-hmm. So let's say you need to find that angle here. How are we going to find that angle? 10, right? Because if you are sitting here, it's you here. This is the opposite side. This is the adjacent side. So the angle will be 10. And then you have 5 over 15, which is 18. Do you all agree with that? 18 degrees? Right? Yeah. Yeah. So 18. So this is 18 degrees, right? But if I want to use the standard notation, okay, so I want to take this angle there, right? From the positive x-axis. So that will be 162 degrees, okay? Because you do 180 minus 80. So that will be for the standard notation. If you are confused by that, you print out the polar graph. You take the vector 18 degrees here, and you're going to read 162. Is that clear? What about the magnitude? Magnitude, you have to take the Pythagorean theorem, right? So it's going to be square root of 5 plus 15 square. What do you get? 6.3. You doing it? Don't space out. Something like this, if you use Pythagorean theorem. If you space out, I'm going to add a question about vector on my test. So come back. Do you get that? Square root of 5 square plus 15 square.
I got 15.8.
15.8. So I did. Oh, okay, I did it on purpose to see if real. 15.8. Yes?
Yeah.
Okay, so you have two notations. You can say V. The X component is minus 15. The Y component is 5. Unit is meter per second. Or you can say how much? 15.8 of what? Meter per second, which way? 162 degrees. Because if you say 18, it could be 18 here, it could be 18 there, you're not sure. But if you say from the positive x-axis, we know what we are talking about. Because from the positive x-axis, you go counterclockwise and it's going to be positive. Okay?
Yeah.
So let's go back to here. I take that vector here, right? You can play with it. And I can show the components, right? So that will be the x component, the y component. And I can attach the tail to the origin, x component, y component. Do you see how it works? Or I can do that, okay? I run, that will be the x component. I rise, that's going to be the y component. And it makes like a rectangle. Makes a rectangle, right?
Mm-hmm.
X component, negative 15, y component is 10. Any question?
No.
Okay. Oh, look at that. Beautiful. And you have a right angle triangle, right? This is a right angle. Okay, so let's see what next. So any motion can be divided into two components. And why do we use vector? So vector, so here is an example. Do you remember the airplane? I think you're gonna have one question like this, right? So the airplane, or you are walking on the moving sidewalk, right, in one direction, and the sidewalk is moving in the opposite direction.
Yes.
You have to subtract. If you are moving in the same direction, you need to add. Or you know what will be a very good demo is that if you go on the treadmill, right? So let's say you have a treadmill like this, but instead you walk in the opposite direction. So the treadmill is going this way, you're going that way, right? So relative to the treadmill, you are moving, but someone looking at you, if you match the velocity of the treadmill, you're gonna be at zero. You're gonna be at rest, obviously, because otherwise you're gonna fall. So you don't even need to do computation. Your gut knows the physics, right? You know that you have to match the speed of the treadmill, otherwise it's gonna not end well, right? So just an idea. But because if you are in physical science, for example, if you walk backward, right, on a treadmill, it's very good for the knees.
Yeah.
That's oldness speaking. So here, relative velocity, you see that the airplane is doing two things at the same time, right? So it's moving relative to the air, right? So it has a velocity relative to the air, but at the same time, the air is moving to the left relative to the ground. So as a result, the airplane is going to move in this direction. So you can think of that as the y component, that will be the x component, and that will be the velocity of the airplane relative to the ground. Does this make sense?
Mm-hmm.
It's like the airplane says, I want to be here. And then the wind is pushing and say, no, you don't. You're going to be there. When you are doing this is called tail to head, and this is called adding vectors. We're going to get back to that in the next unit. So one way you can visualize this business here is with this app. Reset. Okay, so here you have a boat, right? And the boat has engine. So it wants to move in this direction, right? So it has a velocity relative to the river. Agree? But the river is also flowing in that direction. So the river has a velocity relative to the ground. What's going to happen to the boat? Right? In diagonal, right? It wants to go this way. No, you don't. Okay, you're going to be pushed on the side. That will be the sum of the two vectors. So let me show you. Ready? That's what's going to happen. And you're going to end up here. Does it make sense? So everything happens like relative to the ground. The vector has two components. One component that will be the y component, and then the x component, and that will be the final velocity. This is the velocity of the boat relative to the river. This is the river relative to the ground, and that will be the velocity of the boat relative to the ground. Does it make sense? So this is called adding vectors. You see? So if you don't know what you are doing, you're not going to get to the point here. So what can we do? I don't want to go here. I want to be there.
You go.
Very good. Moving to the left, right? I can do something like this, right? You see what I'm doing? Okay. So it means I'm going to move in this direction, and the river is going to move in that direction. So that will be the final result. Let's see. Okay. So why do we need to know that? Because, for example, if there is a ferry crossing the Hudson River, for example, in the software, they have to take the current in account, right? So they have to measure how fast the river is going, which way you need to drive to make sure that you get at the dock, right? Otherwise, you're gonna miss it. Okay, another example in sport, also very important, they use a lot of physics to develop all those softwares to help athletes, to perform the best. So for example, if I have a football, do you say a football like the ball, a football ball or football? Yeah. You say football? Ball. A ball. Okay, you have a football in your hand and you're gonna start running in this direction, right? And at the same time, you're gonna throw the ball perpendicular to your direction. So do you see that the ball is doing two things at the same time? It wants to move forward, but at the same time, it's going in that perpendicular direction. Mm-hmm. So which way is going to go? Somewhere in between, right? So that's what you see here. The player is moving in this direction. He's going to throw the ball perpendicular to him, and the ball is going to go in that direction, diagonal. Do you have to take physics 2053 to know exactly where to position yourself so you can catch the ball? No, you learn it by practice, right? And then it's your gut doing the physics. You know exactly where to go to catch it. But same thing here, right? The ball here has two components. X component, you can think of this one as the X component, Y component, and that will be the direction in which the ball is going to go. Right? So this is called, we're going to get back to that in the next unit. This is called adding vectors. Okay? So it's going to move this direction, but at the same time, it's going to move that direction. So the final velocity will be this one. Okay? So next unit, we're going to learn about that. Let me just introduce. So this is called adding vectors. So if I take one vector here, so let's say the player is moving in this direction. Do you agree? But at the same time, okay, he has the ball, the football in his hand. So that will be the direction of the football. What's going to happen to the football is going to go in that direction here. So it has two components, X and Y. So that's what we call adding vectors. Okay, any question? So here, again, same idea. Is doing two things at the same time. It wants to go in that direction relative to the water, and that will be the speed. Okay, but at the same time, the river is pushing in this direction. So it's doing two things at the same time. So that will be the final direction. Is that clear? So, question for you. If you know that the river here is 1,000 meters wide, how can I find the time it takes to cross the river? Which component should I use? The y component or the x component? The not so I want to know. I use both. Okay, if I know the diagonal, the distance covered over the diagonal. I don't know that. I know that this is 1,000 meters wide. So I know, if you want, the y displacement. So if you have the y displacement and you have the y component, so which one you're going to use? The y component. Even though you start here, you're going to end up there. So if you have that distance, I agree with you. You're going to use this here, right? The final velocity. But if you only have the y displacement, so that distance here, which is 1,000 meters, then you use only that component. This is the whole idea. What's so funny? I don't know, it's always laughing. So if you use the excuse me, what's so funny? I know you keep laughing. No, nothing funny. Because if you share, that would be nice. It's funny. So if you are just given 1,000 meters is how wide is the river, then you're gonna use the y component of the vector, right? So let's review for the test. Can you find how long it's gonna take to cross the river? So you can think of that as the y displacement, right? So you go from here to there. So that delta y is 1,000 meters. Okay, so you're gonna only use the y component, and the y component is 4 meters per second. So how can you find the time? Yeah, 1000 divided by 4. Do you all agree?
Yeah.
So that will be 250 seconds. And then if you divide by 60, you're going to get in minutes. So it's about 4 minutes. Okay?
Mm-hmm.
Instead, you could have used, this distance from here. You start from here. You're going to end up there. So you could have used this distance. In that case, you're going to use that velocity here, right? So that will be how far did it go along that direction. And you can also find how far did it go in this direction. Okay? I'm going to take more examples. Any questions? Okay, so we talked about that. So that will be the polar graph. Did we do all of them?
So,
Did we do this one?
mm-hmm.
So vector C, you see, if you have it in the polar graph, you have 205. So if you want to find the x component, all you have to do is 12 cosine 205, and the y component is 12 sine 205. Do you agree?
Mm-hmm.
So the x component is going to be negative, and the y component is going to be negative. So let me ask you something. Vector A, does it have a x component?
No.
No, right? Just a y component. And the y component is -8. You see the tail is here. That will be the head. And the head is showing you the x and y coordinates of the vector. The x component and the y component. So if you have the vector b, okay, that point here, that point that it is showing you, that will be your x coordinate and the y coordinate. Do you want to do another one? Let's see. Let's do B. Let's do B. You can help each other. Try B. Sure. B, you have two ways to do it, right? I mean, you have different ways to do it. So the magnitude is 15. The tail is attached here, and you have that angle there. So you have different ways to do it. You can say B, the magnitude is 15 meters at 40 degrees. So 10, 20, 30, 40 will be 320. That's one way. But you can also say 15 at -40. That's also legit. As long as you start from the positive x-axis, you can go counterclockwise or you can go clockwise. If you go clockwise, it's going to be negative. So you can do both. If you do it this way, either way, the x component is just going to be 15 cosine 320 or 15 cosine -40. It will always work, only if you start from the positive x-axis. And make sure you are in degrees and not in radians. That's going to be 11.5. Did you get that?
Yeah.
Okay, so 11.5. And then the y component is going to be 15 sine 320 minus 9.6, something like this. And units, meters. Okay? Now, you can also use your trig skills So in that case, if you are good at trig, you could have said this is a cosine 40 and that will be a sine 40. But if you do the sine 40, don't forget the minus here. Okay? How to show the components? You start from the tail, you go to the head. So first you run, so that will be 11.5. And then in that case, you fall, which is 9.6. Or you do the opposite, okay? You fall 9.6 and you run 11.5. So this is a rectangle and that will be the diagonal. Is that clear? This is also called adding vectors. I'm adding X component, Y component, I'm gonna get B. Okay, that point here, the point that you have here, this is the head. Don't cut the head of vectors. Don't do like in the 1789 off went the heads at that time. Okay, so let's practice. Why don't you do the first one? You can help each other. The first thing you want to do is to draw. You draw the situation. Always in physics, you draw the situation. If you have last minute questions tomorrow, I have a test for my astronomy class. I'm going to be in AC2115. You just have to find the door. You have two doors. AC2115 next to the forum. And 10 a.m. you can find me up to 10:50. So if you come at 10:50, I should still be here. But then after that, I leave. So anyway. So west, this is west. And this is east. And this is north. And this is south. So the first thing, 36 west. So 36 west. So it's going to be 10, 20, 30, 36 here. And then you say 22 north. So you go up, out here. So that will be your X component, so minus 36. That will be your Y component, 22. So that's going to be your head. The tail is always at the origin. So that's going to be your vector here. So the first thing you want to do is this. Why? Because then you can get confused with the angle, right? So this is like that theta here, and then here you have alpha. So you don't want to mix them up. So you want to know which side is the opposite side and which side is the adjacent side. So that's why you really have to draw. Okay, so let's find the magnitude. So magnitude, you use Pythagorean theorem, right? So it's going to be 36 square plus 22 square, and you get
42 meters.
42?
42.
Meter per second. So that will be the speed. So it could be a projectile that you launching with that speed, initial speed, and then you find its X component, so how fast it's moving forward, and you find the Y component, okay? It means how fast it's going up. Let's find that angle here. So you have a right angle triangle, huh? So tan is going to be what? Opposite is what? what, right? 22 over 36. So the angle is 31. Do you all agree? I'm gonna make it like 30 degrees, but it is 31. Okay? Is this the standard notation? No, right? So you need to start from the positive x-axis and you go counterclockwise like that, right? So if you are not sure, you can use your polar graph, but otherwise that's going to be, this is 180, 180 minus 30 is 150, 149 if you take 31, you're right. Do you all agree with that? Okay, so you have two notation. V has x component is negative 36, y component is 22 meter per second, or I can say V has a magnitude of 42 of what? Meter per second. Which way? 150 degrees. Okay? Now, in this case, you could have say 30 degrees north of west. This is but that will be just for the homework. Okay, even for test 2, not going to be dealing with northwest, east, north, south. But otherwise that will be acceptable too. So the military people, they will always use the angle smaller than 45. So this is 60 and that will be 30. Is that clear? So if you have a projectile motion, if you throw something like that, that will be how fast it's moving forward at a constant velocity. And that will be the initial velocity up. When it's like you toss something up, it's going to slow down, stop, and pick up speed again. Okay, so this one is easy. So horizontal. Horizontal means the x-axis. So you have a jump. And that will be, no, that's 20. And that will be 25 degrees. Okay? So it has two components, x component and then y component, right? So you have the y and the x. And that will be counterclockwise here. So how can I find the x component? Cosine, right? So it will be 20 cosine 25. Do you all agree? And so it's going to be 20 cosine 25, which is 18. Okay? And the y component is, if you have any question, let me know. Okay? Sine 25, 8.5. That will be the head. So 18, 8.5 meter per second. You run and then you rise. Okay? Okay. Any question, let me know, okay? So, for example, if you have an airplane, okay, it's doing two things at the same time. Let's say it has a constant velocity, so that will be the magnitude, 650 kilometers per hour. So imagine you have a sun here, so you have the shadow of the airplane on the ground. You can find how fast is the shadow moving along the ground. That will be given by the x component. And then if you are located here and you see the airplane going up above your head, you can find how fast is it moving up, right? Going in the upward direction. So it's doing two things at the same time. It's moving forward and up. And you can totally decompose that motion into two components because it will make easier to compute, for example, the x displacement, the y displacement, or the height. Okay? So here I forgot to put numbers, so let's go to here. So Newton is a unit for force. So you see dad is pulling here, and that will be the vector force. So it's a vector. So it has two components, right? It has a x component here, and it has a y component. Question: which component is responsible to make the cart here moving faster? The x component, only the x, right? So it means if there is no friction, you're going to have an acceleration, right? Because you remember what I told you, acceleration is always proportional to the force. Okay, that's how you know which way it's going to be. Okay, and then the acceleration here is only along the x. It's not going into space or inside the earth. It's accelerating along the x. And the component responsible for that is the x component. Now, why do we have a y component? What's the job of the y component? To lift, right? Mm-hmm. So if you have something heavy like that desk, it's easier to pull and to push. Why is it easier to pull? Why do you want to lift it?
Less friction.
Less friction. You decrease the friction. If you push, like if I have a desk here and I push, I'm going to push it into the ground. So I'm going to increase the friction and make it harder. My point is, vectors have different jobs. The job of the x component is to make it move forward, accelerate, because there is a force. And the job of the y component is to lift, right? To decrease friction. So how can I find the x component? Cosine, right? So it's going to be 50 cosine 30. And the y component?
50 sine.
50 sine 30. Do you all agree with that? Right? And you see here, that will be a horizontal displacement. Okay, so here you have a displacement. So we're going to use that a lot. It's also important for muscles, right? When you have a muscle, it has components, and the two components don't have the same jobs. So here is something interesting. Let me show you a picture because otherwise it's hard to see what's going on. I think they have it at Miami Beach on the sand. Do you have that? Have you seen that? So you have some kind of car with 3 wheels and you have a sail. So it's like sailing, except you do it on the ground, right? And you are using the wind. It's a sport. And you see how it's lifting off the ground? You see that? So let's look how it works. So here you have that car. And no, it's not good. Okay, that's better. You see here you have the sail. Here, you have the sail here. You see that? And you have 4 wheels. One wheel's here, one wheel, and one wheel, right? And it wants to move forward. So what's happening? You have the wind. They make the wind. This is Mr. Wind. So that will be the force from the wind. Do you agree with that? It's perpendicular to the sail. But can you see it has 2 components? Right? So that force has 2 components. One forward and one here perpendicular. So that will be X component and that will be the Y component. Which component is responsible for the forward motion? X. What do you think this component is going to do? Tilt. It's gonna tilt, right? It's gonna tilt off the ground. That's why it's fun, by the way. That's the whole thing. That make it also very dangerous because you're gonna go if you have a lot of wind, you're gonna go really fast and off the ground it goes. That's the thrill, right? So that's why you have 2 components. One component is going to lift off the ground, and one component is going to make it forward, accelerating. Okay, Usain Bolt. Okay, let's look at Usain Bolt. He is a sprinter. Have you heard of him?
Yeah.
Like amazing, but he's retired now. He was very, very good at running, sprinter. And what you see here, so the idea is to get a very, very, very large acceleration at the beginning during a very small amount of time. And that's what he was good at. He was able to deliver a huge amount of power during a very small amount of time. So you see, when you push here, you push on that support. So the support is pushing back. So you have the force here. So you want to make sure that force here will have enough X component here to push you forward. That's going to give you the right acceleration, right? You want to have a huge forward acceleration, but you cannot make it all horizontal because otherwise you cannot leave the ground because gravity is pulling you, right? But at the same time, you need to have a Y component to lift off the ground. But you want that is the component that will give you enough forward acceleration. So you have to make it right. Is that clear?
Yeah.
Because we don't have 4 legs, unfortunately, right? So we need that component here to help us fighting against gravity. And you see the center of mass here. Center of mass has to be forward also, right? To get some momentum forward. So a lot of physics in sports. So, for example, you're going to have one problem like this for test number 1. So it's a projectile motion. I'm not going to go over it. You can always go back to YouTube and I took you step by step. But you see here, you have an airplane moving at a constant velocity and it's going to drop a crate, right? So the crate is going to keep the same horizontal velocity. Along the vertical is going to be in free fall. Do you remember this problem?
Mm-hmm. Yeah.
But now I gave you the answer kind of without much explanations when it comes to the final velocity. At the end here, okay, before it's going to hit the ground, you see the velocity here, the velocity has 2 components, the 150 that it wants to keep all the way through the motion. And it also has have a Y component. Do you remember?
Mm-hmm.
So the Y component was equals to initial velocity is 0. Okay, it's not being pushed down. And then you have minus 10, and then the time here, right? How did we find the time? Because we knew the Y displacement. Remember this problem? The y displacement was nya 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 nya. So that was minus 1050. Initial velocity is 0 here because you don't push down. Minus 5t squared. So you find the time. And here you can find the final velocity 145. So this is called projectile motion. Along the y, it's free fall. Any question on that? Remember that?
Yeah.
The velocity will change at a rate of negative 10. So now, can you find the, so you have the x component, you have the y component of the vector. Can you find the magnitude and the angle? See, I'm gonna plot the head. So 115, and here it's 145. So that's the head. The vector goes from the origin to the head here. So what was the magnitude? You use Pythagorean theorem, 185. So that will be the final speed. Okay, so that is in the real world. In the real world, you're not going to say, oh, what's the x component, that's the y component. That's just for the computations. In the real world, you're going to say, what is the final speed before it's going to hit the ground? The final speed is going to be 185. The real world. Now, we want to find the angle here relative to the positive x-axis. And it's okay to go clockwise. If you go clockwise, it's going to be negative at the end. If you go counterclockwise, you can do that too, and it's going to be positive. Let's find that angle here. So you have a right angle triangle. The right angle triangle. So tan, opposite, 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 opposite. So 52 degrees. So this is 52 degrees, but relative to the positive x-axis, it's going to be, so I can put 52 degrees, okay? But when I'm going to write that down, so velocity has a magnitude 185 meters per second at minus 52 degrees. Okay, that's one way. Or, yes. How much is that? 308, thank you. That will be the difference. You can use a polar graph, or you can do, so that will be minus 52, or you can do counterclockwise. So this is counterclockwise, this is clockwise. Clockwise negative, counterclockwise positive. Yes. What did I get, the what? The 2?
Oh.
That's 52. Right?
Sorry about the bracket. It says 10. That's the able chart.
Oh, that's an alpha. That's my rate. That's my 2. I don't have a little loop here. No, it's an alpha. Sorry. Okay? What do you think here? So you are pulling a block. Okay? It has X component is 10 pounds. Y component is 10 pounds. What's the angle? It makes like a perfect square. It's going to be 45 degrees, right? So when the sides are equal to each other, it's going to be 45 degrees. Otherwise, you do tan, arc tangent. 10 over 10 is 1, so it's going to be 45 degrees. Okay? Any question? So that's for vectors. So now that's not on the test, okay? That's another type of projectile motion. Okay, so it won't be in the test, but if you are taking the MCAT, you might have question on that. But it's really not hard. Okay, it's still going up and down. At the same time, it's gonna move forward. So you have two motions combined together. You have forward at a constant velocity, and then you have free fall with an initial velocity up. So if you throw something up, it's going to slow down, stop, speed up. So you see at the top of the trajectory here, it has no y component, just x component. So you can see the two motions happening at the same time. It's moving forward, 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 forward with the same velocity, but it's also going up and down. So once you understand that, it's not that hard, except that when you are launching a projectile, you see it has an initial velocity that has two components. One component is along the x, and it will stay the same, stay the same, stay the same, stay the same, stay the same. And y component here will decrease, decrease, go to 0, increase, increase, increase. So if I have like, so for example here, what's the initial speed? Do you see? 15. What's the angle above the positive x-axis? 35. So how can I find the initial x component? Cosine, right? So I'm going to do 15 cosine 35. That will be the initial x component. The y component, I'm going to do 15 sine 35. And then I can decompose my motion into two components, right? Let me show you. Fire, no, you go too fast. Go back. I cannot go back. No. You can have a bit of slow one. Ah, slow. Thank you, thank you. Velocity. Okay. So you see, initial velocity is just okay. In that case, it's just. But we already did that. I don't want that. I want with the angle. Okay, that's better. So ready? Slow. You see the initial velocity here. It has a y component and the x component. Look at the y component, 0, and then it's going to increase again. That will be the velocity at a given time. It has a y component and x component. So this is the full projectile motion. So I'm going to show you how to do it, but I'm not going to do too many of them because experience shows that those who get it, they get it very quickly, and those who don't get it, they will never get it. So it's no use. But don't worry. This one won't be on the test, okay? So projectile motion, okay? X component stays the same. Y component is going to decrease, get to 0, and then increase again. Example. Okay, so I have this example here. Okay, so it's a nice projectile motion. So if I ask you conceptual questions, so what kind of curve is that? Parabola. Parabola, very good. Now you see the time to go up will be equals to the time to go down. Do you agree?
Yeah.
Okay. And that will be called the range. Okay, so that will be the x displacement. The maximum height is called the y displacement. That will be your initial velocity, which is 22. And then the only challenging part is to be able to find the x component, which is 22 cosine, and the y component, which is 22 sine. Once you do that, you see you use the same methodology, meaning along the x, the velocity is not going to change, and I'm going to use that equation here. Okay, the x component stays the same, and along the y, we are back to free fall when you throw something up, right? So if you throw something up, 50 meters per second, and then it's going to be 40, and then 30, 20, 10, 0, and then 10, 20, 30, 40, 50, right? So how do we find the maximum height? We say that at the top, the velocity equals 0, right? That will be also to find the time it takes to go up, which is the same time it takes to go down. So that's a review for the test, right? Like if you need to know if you toss something up, you slow down, stop, and speed up. So you do exactly the same thing here. Okay? So you have those equations here, which is for free fall, except the initial velocity will be given by the sine. So you can find the time it takes to reach the top, then the total time, and the maximum height. Okay, so those who are taking the MCAT, for example, you might want to look at that. Otherwise, don't worry. For the test number 1, we only focus on horizontal velocity to begin with. No vertical velocity to begin with. And then it's going to go down. Is that so if you're interested, you can help him if you want to help him. So I'm skipping that. So sometimes in your textbook, you can see they give you an equation for maximum height and for maximum range, for the range here, right? So this is called the range. How do we find this equation? It's not that hard. You malax and massage the two sets of equations, you're going to get that. Just have to trust me. You don't need to memorize anything. Do you agree? Okay, so do you remember what's the maximum range? Like for a given initial velocity, what's going to be the angle?
45.
45 degrees. Very good. You remember the demo I showed you? 45 degrees. Why is that? Because you see, this is the range. Okay, it depends on the initial speed square sine of 2 times this angle here. 2 times 45, how much is that? 90. Sine 90 is, sine 90 degrees is 1. So the maximum range will happen when sine equals 1, because the maximum value of sine is 1. And to get sine equals to 1, that angle here has to be equals to 45 degrees, like we have seen before. Okay? So what I'm getting at, I just want to show you that physics can be very useful for sport. There is a whole branch, biomechanics and things like this. So here you have Usain Bolt, right? He's a very, very good sprinter. But he only did sprint, like he was only running. But you have another discipline in the Olympic Games. You have also the long jump, right? And the question is, if he had decided to change his discipline, you can do that. What will be his jump? How far will he be able to go? That's the question. Do you understand the question? Mm-hmm. Even though he was a sprinter. So how far could he go? So it's like a projectile motion. And you see how far is given by this equation. Okay? So it depends on the speed square. It makes sense. It depends how fast you start, right? Here, your initial velocity. And it depends on the angle here, right? Do you agree? Mm-hmm. Okay. So next, you see these are the athletes who did the long jump. And it's how far did they jump, so from here to there, as a function of their initial velocity. So they have an initial velocity and the jump. And this is how far is the jump. And the world record here is about 8 meters. Okay? Not Usain Bolt. Usain Bolt he was a sprinter. Do you agree? Mm-hmm. So let's use that equation to see that if Usain Bolt had he decided to move to long jump, how far will it be able to go? So what do we need? We need his speed. Do you agree? Mm-hmm. And then the angle, it's impossible to jump at 45 degrees. Try. If you get 45 degrees, I will give you extra credit. But usually you can't. The angle, the best you can do is about 33 degrees. Okay? And what about the speed? Oh, by the way, let's review. Let's review for test one. Here you have the time, and here you have the distance. So this is just for Usain Bolt. So that will means that 20 meters, he did that in 3 seconds. And then, I don't know, 60 meters, he did that in 6.5 seconds. So you have that graph here. How can you find the speed? The slope. Slope, very good, right? You look at the unit, meter per second, that will be the speed. So you find the slope. And what's the rise here? It's about 20. It's about 20. Is that 20 here? From here to there is about 20. And from here to there is about 20. And is that 1 second or 2 seconds? 1.5? So 20 divided 1.5?
13.3.
13.3, about that. That will be his speed, which is very fast. So, but so 12.1 is actually his speed, 40 meters. So 12.1, the speed of Usain Bolt. 15 degrees, 15% loss. So we're going to say the speed is 10.3. The angle is 33 degrees. So can you use that equation to know that what will be the range, okay, of the long jump will he decide to switch? Okay, so you want to use this equation here. Okay, you have the speed of Usain, 10.3. You have the degrees here, 33 degrees, but you need to multiply by 2. And here it's about 9.8. Okay, so D equals, you plug it in. It's just to know if you know how to plug it in. So you have a 10.3 square. Here you have gravity, so 9.8 times, and here you have a sine. Inside you have 2 times, so 2 times 33. 9.9?
Yeah, 9.9.
Do you all agree or you want me to do it? So 2 times 33 means 66, right? So sine 66 times 10.3 squared divided by 9.8. Yes? Mm-hmm. So look, it will have been here. So this is the world record right there, and he will have been here. Will he have decided to change his discipline? So just to give you an idea of the athlete. He's retired, I think. I think he's retired. But amazing athlete. So anyway, my point is what's the point to take physics, right? That's the point why. Okay, you can use that in sport. And again, we were trying to find the range, the farthest. Okay, and how far depends on the angle here, this angle here, and the initial velocity. Any question? You know that the test is coming when you see all those empty states. Any question? No. So, okay, typical conceptual question, not for this test, for another test, is called the monkey business. Here is the question. You have a hunter, right? And there's a monkey there. And as soon as so it's like a projectile. Okay, so as soon as the trigger is pulled, right, there is a noise. So the monkey gets scared and falls, right? So as soon as the projectile here leaves the gun, the monkey let go and falls. If you want to hit the monkey, do you want to aim above the monkey, at the monkey, or below the monkey? Knowing that both the projectile and the monkey are falling under the influence of the same gravity because they are both on Earth. So below the monkey, above the monkey, at the monkey. So you say below. So it has to do again with two components being independent from each other, right? So let's do the monkey. Where is the monkey? Do you see it? Project monkey. Okay, so now we don't want to offend anyone anymore. So it's not like killing the monkey, it's feeding the monkey. So let's say I'm gonna aim below the monkey. Nope. So what do you think? Below, above? Nope. At. Let's see. At. So it's at. Why? It's a typical problem in physics. So the projectile here, okay, it wants to keep going in a straight line at constant speed, right? So it wants to be here. No, you have to fall, right? So it's falling one. Because there is gravity, but the monkey is also falling one. I want to keep going straight line at a constant speed. I want to be here. No, now you have to fall 4, right? So 1, 2, 3, 4. And now the monkey is also falling the same thing. 1, 2, 3, 4. I want to keep going. No, you have to fall 9, and the monkey will also fall 9. So because they are acted upon gravity, both of them, what's happening along the y-axis does not care what's happening along that direction. They are independent from each other. So you have to aim at the monkey. And so there was this MIT demonstration, very famous demonstration. And no one was injured, so it's not a real monkey. Don't worry. Don't get me in trouble. I don't want to hurt monkeys here. So what's happening here? So it's a gun, a golf gun, right? And here you have an electromagnet. So as soon as the gun is fired, the electromagnet is turned off, and the monkey is going to fall. So the monkey and the golf ball are both falling at the same rate, right? So let's see. It's a stuffed monkey, okay? Don't worry. So there is a laser, so you want to make sure you aim at the monkey. So, see that? So it's a typical demonstration that we usually do for a physics one, right? It's not that intuitive. So if I ask you for a conceptual question, you will know at the monkey, right? Mm-hmm. Any questions so far? So I'm going to start circular motion. Circular motion. So let's say you have, let's say you are spinning. If you have any question, let me know, okay? Like something like this, right? So you have a load, right, attached to a string, and you turn this to you swirl the string like this above your head, right? Now, if you let go, where do you think it's gonna go? Is it going to be in this direction, or it's gonna go in that direction? Tangent, okay? Because of something called inertia, right? So if there is no force acting, it wants to keep moving, okay, in the same direction at the same speed forever after. If you want the object to stay on a circular path, you need what is called a centripetal force, right? Something to pull the object toward the center. Centripetal means toward the center, right? And I'm going to show you. That can give you ideas for a demo. But basically, it works like this here. I want to keep going in a straight line at a constant speed. No, you can't. Okay, there is a force here pulling toward the center. And faster it goes, stronger has to be the string. If you start to spin really, really fast, the string is gonna break. So I want to keep going in a straight line at a constant speed. No, you can't. There is a force here. So if you want something to move along a circular path, you need a force. We call that a centripetal force, right? Because otherwise, off tangent, it goes, right? So I'm going to show you a demonstration that I found that really, really explain the centripetal force. So here, that will be the force applied, and that will be the circular path. So if you have a bowling ball and there is no friction, the bowling ball wants to keep moving, okay, in the same direction at the same speed along a straight line forever after. So where is the force? He has to apply a force toward the center. That's why it's called a centripetal force. If he stops applying this force, off tangent, it's gonna go. So if you want something to stay on a circular path, you need to apply a force, right? A centripetal force. Otherwise, off tangent it goes. So likewise, if you are making a turn, okay, on the highway, like all those people, crazy people driving on here, if you go too fast, okay, you make the turn, what's gonna happen to you? Right? Off tangent you go, because what is providing the centripetal force when you're making a turn? The what? The tire. So the force is between the tire and the road, right? So what do we call that? Friction. The friction, the static friction. So if it is icy, or here cannot happen, but aquaplaning, if you have aquaplaning, for example, off tangent you go because you do not have enough friction to push the car toward the center. So this is called a centripetal force, right? So let's see, I have a small demo somewhere that I found here. No. Start over. So typical conceptual question, right? So you have this, it's going to go around, and here it's going to leave the track. Question, is it going to hit this box, to hit that box, or is it going to keep going in a straight line at a constant speed?
Straight
line.
Exactly, right? So it's going to go like this. So whatever it was doing before, it wants to keep doing it. The reason it's going to stay on track here is because there is a force here pushing from the wall here. It's going to push the ball toward the center, right? So that's a typical. So let's see if I have 3 minutes.
Potential question.
At what time does it open, the pop quiz?
30.
30. Okay. Yes.
So the same, like, so like the sun, for example, the gravity, it's like the same force acting upon the planets, right?
Mm-hmm. So that's a good question. So for example, if you have I like to talk about the moon. Let's take the example of the moon. How come the moon does not crash on the earth? Actually, the moon is always falling toward the earth, right? It's in free fall. So this is the moon and have the earth. So the moon wants to keep going straight line at a constant speed. No, you can't. Gravity is pulling in, which is the centripetal force, right? I want to keep going straight line at a constant speed. No, you can't. There is gravity pulling in. I want to keep going straight line. No, you can't, right? So the orbit is going to be a circular orbit, and the centripetal force is gravity pulling in. Without that speed here, it will crash. So actually, that was the genius of Newton. He was able to show that actually the moon is actually falling toward the earth, but it never reached the earth because the earth is curving away. So he says it's the same force acting on the moon and acting on an apple, right? So the moon and the apple are both falling toward the earth, except that the moon never reaches the earth, right? Okay, so I'll finish next time. So you do have a test on the